Hello, hello. This is lecture 12. Yes, it is. It is lecture lecture 12. Yes, and I'm very excited to bring you lecture 12. I am. Remember, in the previous lecture, we left right off at Kirchhoff's laws, right? Oh, it's so cool that we should just go right to the share. Remember, this is the OpenStax physics textbook, which we'll refer to a fair amount for this lecture as well, because it's an extension of the cool stuff that we were doing up to that point about circuits, right? Specifically parallel and series circuits in direct current, DC circuits. We had just left off on Kirchhoff's rules, as you can see, right? Which are basically conservation rules about how much current coming into a junction, right, has to equal the amount of current coming out of the junction. And then the second idea that the total amount, any closed circuit path, right, any loop for a current, excuse me, for a potential, right, the voltage has to total up to be zero, right? So this is an important part of what we were talking about in terms of circuits. And remember that I told you in the previous video lecture that it's not an easy thing for me. And I want you all to take your time with it. It's complex, but it's not difficult. So take your time with it, learn as much as you want to and you can with it, and we'll move on to do other cool stuff, even though I'd love to tell you more about great stuff. So here's the deal, right? This was where we left off in Kirchhoff's rules, but now we're going to add into these circuits an extra piece of equipment. Now, remember at the introduction to chapter 19, there was that little video that I talked about that talks about, draws a circuit diagram of a capacitor on one side with a battery and then a resistor, in that case, like the human heart, because it was talking about defibrillator and how you can move current or joules, basically energy, or even charge, more accurately, from a capacitor into a resistor in the same way that you might move charge from a battery through a resistor, but they do different things. And so we're going to talk about that because this is a very cool and important part of science, especially if you plan to use something like a defibrillator, or if you like disco, I like to boogie, I like the disco, and they have strobe lights and stuff. You want to know how that all stuff works? Yeah, this is where we are doing this cool science. Okay, so let's have a review. All right, I've just made this little back of the envelope-ish thing here. Remind you the difference between capacitance and resistance, right? The capacitance of a capacitor, right? C, capital C, again, not to be confused with coulombs, which is actually the amount of charge, is Q, charge, right, divided by V, voltage. The amount of capacitance in this thing is the charge that's in it divided by the voltage, the electric potential difference between across them. I gotta say, a little bit embarrassing. In a previous back of the envelope, I actually wrote this wrong. I wrote C equals V over Q. Very embarrassing. I knew what I was talking about, but whatever I wrote down was totally wrong. So anyway, hopefully I'll go back and fix that at some point. But just remember, this is actual capacitance, right? It's charge divided by voltage. And notice that the units, I'm just going to hold this as still as I can so the camera will focus on it. The units basically come out as coulombs per volt. And if I write it out in these units, coulomb squared per joule is how much it is. And that's called a farad, right? It's a certain amount of capacitance. Now, resistance, right, based on Ohm's law, which is V equals IR, right? Voltage equals current times the resistance. You can divide it out this other way, R equals V over I, which means the same sort of thing. And then that means that the units of resistance is the amount of volts per the amount of current, which is measured in amps or coulombs per second, right? So an ohm can be written as a joule times second per coulomb squared. So that's what an ohm is, and that's the symbol, the capital omega, because it happens to have a nice sounding with ohm. That's a measure of resistance. Now notice that a farad is a coulomb squared per joule, whereas you've got the joule per coulomb squared, got the reciprocal over here for resistance, but it's just got that little second kind of hanging out there. So that makes an interesting point. You know what? I'm going to write an F over here on this green thing just so we can remember what the symbol for a farad is. Right? That's a capital F for farad, right? And in a few lectures, you're going to find out who this guy, Michael Faraday, is, which is cool because that's what we named the farad after. This guy, Michael Faraday. Um, and his invention slash discovery literally changed the course of human civilization, which is quite remarkable. So notice if you Coulomb squared over Joule, and you have the Joule second per Coulomb squared, which makes a very interesting result, which I'm just going to write down because I think it's kind of fun and it's kind of neat to know. If you multiply a farad with an ohm, what do you get? 1 farad times 1 ohm equals what? You take the joules second per Coulomb squared down here, multiply by the Coulomb squared per joule, all you're left with is a second, which is kind of cool. The usage of this is not going to happen in this class, alas. Like I said, there's so much to talk about. If we were in a full-blown physics class for majors, I would go into this in detail and do all the cool math and all the cool connections and everything. And it would be fun. Alas, I regret we're not able to do that in this class. I'm sorry, but I'll try to find the coolness in this physics anyway, without going into that detail. But isn't it cool that if you take capacitance and resistance, two electrical quantities, right, in circuits and so forth, you multiply them together, you actually get just time. Wow. Deep thought. Anyway, to be discussed at some future time. So remind you of what capacitance is. And so now let's go share screen and go back to the textbook, which we're going to use a bit, as I said, during this class, this lecture. And notice we're going to go back to the capacitor. So here's the Kirchhoff's rule stuff. We'll get back to that in a moment. But if you're going to do capacitance in a circuit, let's see what happens. Capacitors in series and parallel. This is section 19.6, as you can see in the textbook. All right. And we've already learned from our previous conversation, right, that if you're doing the capacitance, right, you can hook them up in series or in parallel in the same way that you can hook up resistors in series and parallel. But the behavior of this is just a little bit different from what you might expect. You might think that, like resistors, if you put 3 capacitors in parallel, then you just get 3 times the capacitance, right? And you just get more capacitance because you put more capacitors in between. But that's not how it works. Why? Remember what capacitance is dependent on. If you have 2 plates, which are drawn here, right? One with a positive charge Q and the other with a negative charge Q, and you have the capacitance in here. Q, right, is C times the V, or the capacitance C is Q over V. If you put them in series, though, it's almost as if you're taking these plates and adding the distances between the plates together to make one big capacitor, right? I'm going to stop sharing for a moment. Basically, if you add this capacitor in series with that capacitor, in series with that capacitor, it's like you're putting one capacitor in with this much space in between them. And when you separate distance out, right, the more space you have between the plates in a capacitor, the less capacitance you have, right? This is an odd thing. So that capacitance, it does increase, but it doesn't increase in the way you expect. You actually get less total capacitance because you've increased the space between the capacitor plates, right? That's a net effect. And if you remember, that's similar to a different kind of thing that gets added. So go back and think from the previous lecture. What is it that when you add them in series, you're actually winding up with less because you're doing this? You're adding the reciprocals, right? So 1 over the total series capacitance is 1 over the first capacitor's capacity plus 1 over the second plus 1 over the third, and so on and so on and so on, right? Total capacitance in the series has actually been reduced compared to the individual capacitances of the capacitors that are in the series. So take a look at this and try to work this out and see what happens, right? Here's a mathematical example, 19.9. And look, the capacitance for the entire 3 capacitor series is less. It's 0.775 in this case microfarads compared with each of the individual ones, 1, 5, and 8 microfarads. Isn't that interesting? Well, I think it's interesting. That's cool. All right, so what does that mean? It means that capacitors behave kind of like current in parallel. What? Have I like spoken in a weird tongue and not understand what I'm saying? Well, maybe. It's possible that I don't know what I'm talking about. But assuming that I kind of do know what I'm talking about and I'm looking through this, remember that if you put parallel resistors in a circuit, then the overall resistance, right, is added differently. This is the description of adding resistances in series. The total series resistance is just the sum of the resistances, right, of the individual ones. But as soon as we go to parallel, right, this is the major features of resistors in series, this is what we talked about in the previous lecture. But as soon as you go into parallel, notice what happens. The resistance in parallel of 3 or more, 1, 2, 3, etc. resistors in parallel is actually lower. It's just like this capacitor thing right here, right? This addition here, 1 over C sub series is all the different series stuff. Whereas on the other side, oh man, sorry, I'm having a hard time sharing the screen thing here. All right, with the resistors, right? It's this, the major resistors in parallel. So resistors and capacitors act in an opposite way from one another when it comes to putting them in series and parallel. Isn't that funny? Well, it ain't all that's funny. There's more. Yes, because you can put capacitors in parallel too, can you not? Yes, you can. And this is again in the section 19.6. And we've come back here and notice what happens if you do the capacitors in parallel. Oh, look, the charges are adding now, right? When you have the voltage coming through in this way in parallel, the charges add up. Whereas in the previous thing, it was the charges that's totaled, and you had to bleed off individual charge in each capacitor. Now you've got all of the charges. It's like adding up all the charges on one side and all the charges on the other side together with the same capacitance. No, so in parallel, capacitors add the same way that resistors add in series. Whoa. Okay, so we got to go back here to resistors in series. Resistors in series add that way. Capacitors in parallel add that way. Isn't that neat? I think it's cool. I want you to understand that so that when you're doing calculations, of course, it's very useful to know that you have to make the calculations, but conceptually, just imagine they act very opposite from one another. And why not? You would expect that to happen, wouldn't you? Right? Because you have joules on the denominator here, joules in the numerator here, coulomb squared in the numerator here, coulomb squared in the denominator there. So the fact that capacitance and resistance act opposite to one another, if you look at the units, conceptually speaking, I guess it makes sense. How about that? Okay, so think about that. Hold that in your head for a second, because now we want to put them together in a single circuit. We come back to this back of the envelope. Remember, this back of the envelope is correct, at least as far as I know. I did not make that foolish error, which I'm not going to show again because it's embarrassing. I don't want to confuse you. Remember, capacitance is charge over voltage, not the other way around. Silly me, bad me, bad me. It's okay. We all make mistakes. Hopefully, I will correct it soon. All right, the example of this electric circuit. What happens if you put a resistor and a capacitor in the same time? Now, with the remember what happened with the defibrillator, right, circuit. You have a switch, and in one instance, half the time you have the resistor and the capacitor together in the same loop. So it's like the capacitor is providing the voltage to the resistor. to whatever it's doing. On the other hand, half of the time, if you have the other switch going, you have the voltage source, okay, in this case, like a battery or something, charging, and the capacitor together. So this half, as opposed to that half, right, of the circuits are separated. And that's where you wind up with a really cool thing, because what happens if you put a resistor and a capacitor, together in the same circuit without a battery? Whoa. Like, in other words, just have that, right? Somehow you've charged the capacitor. The capacitor has some charge on it. Then you have the resistor here. Well, the charge, right, will travel and it will come to the resistor. Yes. It will do something. What will it do? Right? This is super cool. And it comes back to this, remember, 1 farad times 1 ohm equals 1 second thing. Watch. For this, make sure, please, to read chapter 21.6. This is where the cool stuff happens, all right, everybody? DC circuits containing resistors and capacitors. Those, because they contain both a resistor and a capacitor, we call them an RC circuit. Now, do not confuse this with a DC circuit, okay? A DC circuit means direct current. AC means alternating current, which we'll talk about in a future lecture. RC circuit is a DC circuit or an AC circuit that contains both a resistor and a capacitor, okay? So it's an RC circuit. Then later on, you'll learn about something called an inductor. Then you can get an LRC or an RLC circuit, which gets even more complicated. We're only going to spend a little bit of time on that, but that's super cool stuff, which you will know. And it will be neat to understand it. Really, it will. I promise you, it is super, super interesting. But for now, we're sticking with RC circuits. What happens, right? Here's your circuit. This looks a heck of a lot, if you remember, like the circuit that I drew on that back of the envelope. If you close this circuit, right, then you have what is essentially a battery over here that has a resistor that also has a capacitor, and it'll go around in series, right? So you have a circumstance where what happens? The voltage on the capacitor will slowly increase to the total electromotive force of the circuit, okay? And the amount of time it's going to take, there's this thing called the RC time. They call it tau, okay? And it can either increase in this case or decrease. So if you have an RC circuit with an initially uncharged capacitor, what happens is the current is going to flow, right? The opposite electron flow, just as we've said many times before, but it's worth repeating, right? Current's going to flow this way. The electrons are going to flow that way. As the current flows this way, right, from positive toward negative, as it goes through, what will happen is that the like charges in the capacitor, that means the positives positive or the negative negative, they'll slow the flow down. At first, it'll go up quickly, but then it slows it down, and eventually the capacitor will fully charge after a long period of time, okay? Now this, if you take a look at this tau time, this is R, the resistance, time the capacitance, and you wind up getting a sort of a decay time, or what they call in this case a charge time. It starts, at first in this RC time, it charges more than halfway, but then it charges less than a quarter of the way, then a less than eighth of the way. So it just keeps going down. Eventually, it'll charge all the way, but almost charges all the way to the top. But it just goes and reaches the electromotive force level at a fully charged. But actually, mathematically, right, that's actually asymptote, and it barely reaches it. So if you're using this RC time, right, it's the time constant, it gives you a sense of how long it'll take for this thing to charge. And it has a factor of E to the -1, which is 1 over E. Remember, E is 2.718281828, etc. And so 1 minus 1 over that number is, which is that number here, is 0.632. So you have a time that it will rise, right? The RC time, it goes up to that value. And then the next time it'll go another 0.632, and another time another 0.632, and so forth. So that's how you get a capacitor to charge. Now, what happens when you get a capacitor to discharge? All right, remember that if you have a capacitor, right? You have the resistor over here. In this case, you're charging it, but the resistor is kind of messing up the charge. It's charging up slowly. If you had no resistor here, it charges up rapidly because the charge immediately goes on the capacitor, and then the plates immediately start up getting more charge. But the resistor will cause it to slow down, and it will charge slowish. And remember that most typical resistors have most typical wires have resistance, so there's always going to be some sort of time that it gets to charge all the way up. But the discharge is the cool part, right? If I don't have something in there and I have stuff on a charger, then it will discharge in the exact opposite way using the RC time, right? It goes down by a factor, the 0.632 the first time, and then down by more, and then down by more, and down by more. So you have this kind of discharge, and it's a mathematical structure. Okay, and again, it's that 1 over E thing, right? So the voltage on the capacitor, 1 minus e to the minus 1 times the electromotive force. That's the charging part. And then when you're discharging, it's the opposite direction. Now, in this book, right, and in this course, calculus is not required. I know some of you have already taken calculus, so I would love for you, if you have already taken calculus, to figure out, look at this up, okay? There are textbooks and there are things online that show how this calculus works. It is beautiful. It is marvelous. It's so useful, all right, to use the language of calculus to figure this out. But not using the calculus, it's fine too. You still recognize that there is that 1 over E aspect, right? So in this case, it's 1 over E, e to the minus t over RC. All right, so this is 1 over E, but in a kind of a unusually interesting way. Because the 1 over E part, you've got the t over RC in there. And this RC, as again, it's a time, right? Remember how we talked about time? This fun thing, a farad times an ohm is a second, right? It turns out that that is a really key aspect of RC circuits, or circuits in general that have resistance and capacitance. And in all real world circuits, there is some resistance and some capacitance going on. So the 1 F times 1 ohm equals 1 second thing. That's the RC, right? Resistance times the capacitance. Let me just, because it's fun, write down that here. So here is the capacitance C, right? And then this is R, right? C and R. So you can multiply them together, RC, CR, right? So you get RC time. So the RC is a constant. Sometimes people talk about 1 over RC time, right? It's a how much time it takes for things to go down or to go up. And so this is cool. If you want to control, in other words, how fast or how slow a capacitor is discharging, then you just make sure that your 1 over RC time, this RC, right, is either big or small. Does that make sense? If your RC is big, then the amount of time it takes to go down from 1, say, V0 to 1 over E times V0, right, is going to be different from when your R times C is large. And so this is a way to control your electrical device. You want it to charge super fast, all quickly, like a capacitor for a defibrillator or something? Okay. If you want to charge slowly or discharge slowly, so you can produce like a long tail of electrical charge that goes into your resistor, you can do that too. You want anything to go slowly over time, right? So here's an example that was used about calculating capacitor time. It's called strobe lights, right? Like I said, disco ball, something like that. Strobe lights, or like a flash bulb. Nowadays, we use electrical flashes. They're usually pretty digitized. They're in their phones, in your cameras. But in the olden days, you had a flash bulb. Same difference, right? The flash, usually a battery, right, which releases a steady amount of voltage over a long period of time, can't generate enough charge to create a flash of light very rapidly. But if you take your battery and you charge a capacitor, and then you use your flash, that capacitor can release a lot of light right away. And if you keep driving that capacitor with more electricity, like with more voltage, then over time you can get a flash, 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 flash kind of situation, right? Now, sometimes it's annoying and sometimes it's good to dance to. And this high-speed flash photography thing invented by this guy named Doc Edgerton, right? Some of the amazing pictures that you've seen in life, like the penetrating bullet penetrating an apple, or milk drops splattering on a table. Those are cool, cool pictures, and it's fun to see. So I want you to take a look at this so that you know how you can do this kind of problem in the future. All right. But understanding how this all works is really, really helpful. Right? If you want to know how time is measured, you want to measure circuits, and you want to know like how often your pacemaker should flash to keep your heartbeat properly, right? RC circuit, extremely important, because the RC time tells you how much charge is going to be there. It's like a timing signal, right? Doom and down and up. So here, right, is an example of how you can have the sensor and you have timing. The battery charges the capacitor as if the lamp were not there. But then when it reaches a threshold value, right, at a certain point, it immediately discharges, poof. And then it comes down a certain distance, and then it comes up and then down and then up and down. So that you have this bulb that's using the capacitor discharging through the lamp. Isn't that cool? Yeah, so this is fun. And this example, 21.7, the RC circuit in a heart defibrillator, is actually very practical and important. So take a look at this example and understand how it works and why it runs effectively. Okay, so in this particular problem, look, you can get the voltage down in 24 milliseconds, so less than about 1/40th of a second. You can discharge 95% of the voltage, right? And that's really good because you want that super quick shot of electrical energy into the heart so that you can go ahead and do that. Oh, that's a good question. When is the potential difference across a capacitor of voltage, or an EMF, right? These are both voltages. They're measured in volts. When is the voltage or potential difference across a capacitor equivalent to an electromotive force? Anyway, think about that, see if you understand it, and then show the solution at some point. Take a look. Okay, so DC circuits containing resistors and capacitors, this stuff is really neat. It is so much fun and so interesting. We can use it to measure timing, right? We can use it to do flashes and things like defibrillators or tasers, actually. They also have something to do with capacitors and resistors, which you can look up as well. So bottom line, now we know how circuits work when you have a voltage source that's sending the current, right, around in this loop in one direction, and then you have a capacitor and you have a resistor, these two key components of electrical circuits that are worked with direct current. It can be worked with other kinds of current as well, which we'll talk about. The other kind of current being alternating current, which is really fun to do and gets more complicated, but again, not hard, just complicated. All right, let me remind everyone, like I've said before, my own experience with electromagnetism and circuits and so forth. It took me a while to get. All right, so it's not immediately obvious. If this is going to take you a while, don't worry about it. Go with the flow. Don't try to squeeze it all in right away and then try to memorize and do it all that. Really absorb it over time. It's pretty counterintuitive, right? It's not like an immediate thought process. Why would a capacitor, for example, add capacitance in parallel, but actually not add in series, whereas a resistor will add in series in resistance, but it will not add when they're in parallel, right? Why is that? Think about these things, and there are many different ways to try to think about them. Over time, you'll be able to get it better. Okay, do not worry, but remember these concepts. Okay, I'm just going to hold this up one more time because it's something to remember. Capacitance, resistance, right? How they have a differ, and they have this exact backwards relationship. And here's the relationship for voltage, right, and resistance in a series, but it's the other way around if those things are capacitors. And then there's the parallel circuits in there. So chapter 21 is important, and then chapter 19, specifically 19.6. Okay. All right, so that ends lecture 12. Thank you so much for your time. Spend the time, work with this, okay? Absorb it over time, watch other videos. If you have any questions, like I said, it's a little bit complex, but it's not hard. Just have to keep a lot of things straight when it comes to calculating about circuits. Okay, any questions, ask me. Ask your recitation instructor, ask your lab instructor. It's going to be a lot of fun. And when you know this stuff, you know how like electrical devices work. That's some serious power. That's some knowledge that's worthwhile to have, right? Okay, thank you so much. I really, really appreciate your time. We'll see you in the next lecture. See ya. Bye.